In this video, I'll show you how to calculate the reaction forces of a ladder that's leaning against a wall. The question reads, place a 7-meter uniform 150 Newton ladder against a frictionless wall at an angle of 75 degrees. What are the reaction forces at the ground and at the wall and the minimum coefficient of friction of the ground? Let's begin with an illustration. I'll start by drawing out a wall which looks like this. So that's the wall and that's the floor. And a ladder. The ladder is 7 meters. The wall is frictionless and the ladder is at an angle of 75 degrees. In addition, it weighs 150 newtons. Now that we have an illustration, we can discuss what's happening. Now this ladder is leaning against this wall. So there's a force here and it's pushing against the wall. And in turn, the wall is pushing against the ladder. So I'll show that by drawing a vector in this direction. We'll call this vector R. RH. I chose the letter R arbitrarily, and H represents horizontal. Now there is no Y component of this force because the wall is frictionless, so we don't care about the Y component there. At the same time, at the bottom of the ladder, there is a coefficient of friction that is pushing against the ladder as it slides to the left in this direction. In addition, there is a Y component that we need to be aware of. And that Y component is going directly up. I'll call this vector F. And specifically, that's FH for F horizontal, and that is FV for vertical. Now, when it comes to equilibrium problems like these, the sum of all components that are working along the horizontal equal to 0. And the sum of all components acting on the vertical equal to 0. Let me represent that by writing down the sum of F sub x is equal to 0 and the sum of F sub y is equal to 0. Notice that this vector and this vector are moving in the opposite directions. So if moving to the right is positive and moving to the left is negative, and we know that both of these forces sum up to 0, I can say that F sub h plus negative R sub h is equal to 0. And solving for F sub h, we end up with the following equation. This means that these two forces at equilibrium need to be equal to one another. The only Y component that we're concerned about is F sub v. And F sub v would equal to the weight of the ladder, given that we're told in the question that the ladder has uniform weight. So that 150, don't get any ideas, isn't just at the center, but it's everywhere along the ladder. Of course, in order for us to answer this question, we need more information, more equations that will help us get to what we're looking for. And for that, we need to remember that at equilibrium, the sum of all torque values acting at a reference frame need to equal to 0. So remember that the sum of all torque values, which I'm representing by the Greek letter tau, should equal to 0. When calculating torque in a system, you need to select a reference frame. And the reference frame is completely up to you. I'm going to choose the ground, this point that I'm highlighting, as my reference frame, so that all my torque calculations are based off of this point right here. Remember that torque is the component of the force at right angles to the lever, which is this part right here, times the length of that lever. So we have two levers. We have one halfway, so this point, and another lever at this point. To calculate the torque from here, we need an expression that will give us the torque relative to this component, because this component right here is at 90 degrees to the lever. We'll need to know the angle over here. And to find that angle, just pretend that we had a 90-degree triangle. That's 90 degrees, and this is 15. Knowing that is important because if this is 15, which I'm going to erase just so that you can see it better, we can move this vector down here. And so what we would be looking for is that part And let me just draw this out for you here clearly. So we have something that looks like this. So what I've drawn right here is precisely that part right there, and the whole purpose behind it is to find out the magnitude of that vector. We can do that easily using trigonometric functions. We can use sine. Sine represents the hypotenuse, which is what we have, and the opposite length. So I have sine at 15 degrees multiplied to the magnitude of this vector, which corresponds to 150. And that gets multiplied to the distance of the lever being 3.5. Next, we have to find the torque at this point. And the torque will relate the vector r sub h. So in place of 150, as we had over here, we'll use r sub h, and that will be multiplied to a trigonometric function, which we've yet to find. So if that's 75, that's 15 degrees. And over here, that little pocket would be 75 as well. Let me show you what that would look like if I made it bigger up here. We would have the ladder itself, like that, where that's 75. And if we were to complete this as a right triangle, the right triangle would appear like this. We would use sine at 75 degrees so that we find this part. Remember, this part is at 90 degrees to the lever. So sine times r sub h. Remember, sine is a comparison of opposite over hypotenuse. So if that's a reference angle, that's opposite, and that's our hypotenuse. So let me write that down. Sine at 75 degrees, and that's being multiplied to a lever distance of 7 meters. The lever arm completely 7 meters, which is the ladder. We need to add these up. Notice that this vector and the vector that we found here are going in opposite directions. So one of these need to be negative, and it doesn't matter which one. I'll make this one negative. 3.5 sine 15 times 150 minus 7 sine 75 degrees r sub h is equal to 0. We now have enough equations to help us find what we're looking for. In fact, we can easily find out r sub h by isolating for it. Let me go ahead and do that. So I'll bring this whole thing over to the right side, and let me show you what that looks like. Then we divide both sides by 7 sine 75 degrees. Those cancel out. And now we get to use our calculator. Make sure that your calculator is in degree mode. 3.5 times sine 15 times 150 divided by the denominator being 7 sine 75. That gives us the magnitude of the vector, the horizontal vector at the top, being 20 newtons. That takes care of this part. In addition, we need to find the reaction forces at the ground. If it is 20 newtons at the top, then it's going to be 20 newtons here, F sub h. We also need to find the minimum coefficient of friction at the ground. To do that, we will take 150 newtons downwards, which is the magnitude of F sub v. We multiply this to the coefficient of friction, which I'll represent as mu, and that should give us the value of 20 newtons. Therefore, dividing both sides by 150 makes approximately 0.13, and that's unitless. Therefore, Fv and Fh are related via the coefficient of friction, and that's 0.13. And there you have it. That is how to calculate the reaction forces of a ladder leaning against the wall.